So here we are talking about how to use CDF inversion method to find a realization, to generate a realization of a token given the conditional distribution. So suppose the distribution of the tokens is, the token is 1, with, so the first word was probably P1, and the second word was probably P2, and so on. And there are in total M words, and happens with probably PM. So this is given by the conditional distribution that we estimated. So now the problem is we want to generate an actual word. So pick one from 1 of 1 to m. So here we can only generate a uniform random variable. So this is uniform between 0 and 1. Basically, it's just any number equally likely between 0 and 1. We can only generate those on computers. And now we want to generate something that follows this distribution. So it turns out we can do it this way. We can say we'll output J. J is something from 1 to m if the U is between two numbers. This one is the sum of everything before J minus 1, all the probabilities, and this is the sum of all the probabilities before J. So this formula, intuitively, it looks right because the difference between these two is just Pj. So it seems this thing happens with probability Pj, which is right. It can be shown diagrammatically like this. So suppose we have a block between 0 and 1, and suppose this region, so say the height is 1, and this region is P0 proportion of the whole thing, and it should start with 1. And this one is P1, P2, and say this is P3, and this is P4. So suppose we generate a random uniform variable, say it lands here, we want to output 2. And if it lands here, we want to output 3, and so on. But if you actually check the range, if U is between 0 and P1, it's in this region. And we actually output 1, which is correct. And similarly, from here to here, it's actually starting from P1 to P1 plus P2. It outputs 2, so it's still right. And here it's P1 plus P2 and P1 plus P2 plus P3, so it's this. P1 plus P2 plus P3, and we output 3, and so on. So it seems that this scheme would actually, if you just generate a random variable along this line, it's actually outputting the correct thing. So technically, it's something called the CDF inversion. And the CDF is defined, say, on J is just the probability of a random variable being less than J. And what that theorem says is just if you have any random variable, this is actually the same as the inverse applied on a uniform random variable. This is basically what we're doing here. We're just computing the inverse. And the reason that this works is there's actually a very simple proof. So the probability of this thing happening, say is less than J, is just the probability. Because this is the inverse, you can put it on the other side. And since CDFs, if you look at this expression, it's always increasing. So you can apply f on both sides, say f of inverse of u is less than f of J. And this is because our f is increasing. So you can apply an increasing function to both sides of an inequality and still hold. And these two would cancel out because by definition, inverse and the original function would cancel out. And this would become a random variable u is less than some number. So the fact that this is a uniform random variable, what it means is the probability of this uniform is between 0 and 1. this probability of it less than u is just equal to u. So if it's less than this, that probability is equal to this. And this is due to probability of u less than any number, say small u, is just equal to u. And this is how uniform random variables are defined, actually. And this fj, remember fj is the probability. So j less than j. So here we see that the probability of this thing is less than j is the same as probability of j is less than j. So what it implies is that these two are the same distribution.